I welcome you all for the second lecture on Fourier series and transforms. Today we will discuss following topics: half-range expansions, complex Fourier series, and approximation of a periodic function by trigonometric polynomial. As discussed in lecture 1, Fourier series for an even function of period 2L is a Fourier cosine series, and it can be represented by 11. F of x is a naught plus summation over n 1 to infinity an cos of n pi over l x, and the coefficients a naught and an, they are defined by 12. For an odd function, the Fourier series is given by 13. F of x is equal to summation over n 1 to infinity bn sine n pi over lx, and the coefficient bn is given by 14. Let f of x be a function defined on the interval 0 to L. This function may be the shape of a distorted violin string, or it may be the temperature in a metal bar of length L. We will come across such type of problems in boundary value problems. This is also part of your syllabus, so we will discuss these problems in detail in boundary value problem after Fourier series and transforms. Half-range expansions will be used in solving boundary value problems like one-dimensional wave equation and heat equation. So that's why we are discussing this topic. Let f of x be a function defined on 0 to L, and let's geometrically it can be represented by the first graph. Now periodic functions are generally defined over period 2L, minus L to L, or you can say 0 to 2L. So this given function f of x on the interval 0 to L, it can be extended over the interval minus L to 0, and we can have two extensions. So we are basically extending this function as an even function, and at the same time we can extend this function as an odd function. So suppose we are expanding this function as an even function, so we have function f1x. You can see the graph on the left hand side. So minus L to L, we have just copied this function, and clearly this f1x is an even function. This one is called the even periodic extension. Similarly, we can extend function f as an odd function, and we have a new function f2x defined on the interval minus L to L. So for a given function f of x which is defined on the interval 0 to L, we have two extensions, f1x as an even periodic extension of the function, and for this function we can write Fourier cosine series, which is given by equation number 11 and 12. f2x is called odd periodic extension of f of x, and for this extension we can have Fourier sine series, and it is given by equation number 13 and equation 14. Now there are some exercises that how to check that given function is even, odd, or neither even nor an odd function. For example, f of x is x cube, which is defined from minus pi to pi. We just have to draw the graph. I have drawn it on the right hand side. Then clearly this is an odd function. Consider now a function f of x which is x square, and now it is defined from minus pi by 2 to 3 pi by 2. Clearly its period is 2 pi. Now to check whether this function is even or odd, we just redraw this function, repeat this function on the left side and right hand side. We have the graph like this, you can see in the picture. Now just see the graph of the function now from minus pi to pi. Length of this period is 2 pi, and if we just look at this graph, we can clearly see that this function is neither even nor an odd function. So to check whether function is even or odd, always check the graph of the function over the interval minus L to L. Please try the following exercises 3rd to 6th and check whether the function is even, odd or none. Let's consider one more example. F of x is x and it is defined from 0 to half. For this function we have to find out Fourier cosine as well as Fourier sine series, or you can say find the half range expansions of the function f of x defined like this. So let's start with Fourier cosine series. Here the given interval we treat as the half length of the period, so L is half. For this one, a naught is given by 1 by L, 0 to L f of x dx. Substitute the values. Integrated, a naught is 1 by 4. Now a n, it is 2 by L, 0 to L f of x cos of n pi over Lx dx. Put the value of the function and integrate it from 0 to half. After integration, we have the value of an. If n is even, value of the function is 0. If n is odd, then it is given by minus 2 divided by n square plus pi square. So for this function, the Fourier cosine series is given by this one. See the last expression. Now Fourier sine series for this function. Bn is given by 2 by L, 0 to L f of x sine of n pi over Lx dx. Put the value of the function, integrate it, simplify this, and Bn is 1 upon n pi minus 1 raised to power n plus 1, and the Fourier sine series is given by the last expression on this slide. Now there are 2 more questions for you. Try these questions and find the Fourier sine and Fourier cosine series. In both the questions, the function is defined on the interval 0 to pi, that is half range, and now we extend these functions over the remaining minus pi to 0, so that function is an even function and as well as an odd function. Complex Fourier series. Let f of x be a periodic function with period 2 pi and its Fourier series is a naught plus summation over n1 to infinity an cos nx plus bn sin nx, and the Fourier coefficients are given by a naught and bn defined below. To find the complex Fourier series for a periodic function, we just rewrite the usual Fourier series in complex form. And for this, we will use the following 2 results, that e raised to power iota theta is cos theta plus iota sin theta, and e raised to power minus iota theta is cos theta minus iota sin theta. So using this one, we can have cos theta and sin theta in terms of exponential function. So we can say that cos nx is e raised to power iota nx plus e raised to power minus iota nx divided by 2. Similarly, we can find out sin nx in terms of exponential functions. Now we just simplify the terms in the summation, that is an cos nx plus bn sin nx. Substitute the value of cos nx and sin nx in this expression in terms of exponential. Collect similar terms like e raised to power iota nx and e raised to power minus iota nx. Coefficient of these terms an minus iota bn divided by 2, and the second one is an plus iota bn divided by 2. Both of these coefficients, they are constant. Let's call them Cn and Kn. Let's define a naught as C naught. Cn is an minus iota bn divided by 2. Kn is 1 by 2 an plus iota bn. Substitute all these values in the usual Fourier series and we can have f of x is equal to c naught plus summation over n 1 to infinity cn e raised to power iota nx plus kn e raised to power minus iota nx. Now we further simplify cn and kn. Cn is half an minus iota bn. Substitute the values of an and bn. See the integral on the right hand side. We have cos nx minus iota sin nx, the underlined expression. We can rewrite this one as e raised to power minus iota nx. So after simplification, Cn is given by 1 upon 2 pi minus pi to pi f of x e raised to power minus iota nx dx. Similarly, we can simplify kn and we have finally the third expression. It is 1 upon 2 pi minus pi to pi f of x e raised to power iota nx dx. See the expression of Cn and Kn. If we replace n by minus n in the expression of Cn, we get Kn. So we can say that Kn is equal to C minus n. And if in this expression Cn we put n equal to 0, see the third line. If we put n equal to 0, then Cn reduces to 1 upon 2 pi minus pi to pi f of x dx, and this is same as a naught. So finally we have complex Fourier series f of x is equal to c naught plus summation over n 1 to infinity cn e raised to power iota nx plus c minus n e raised to power minus iota nx. In equation 20, we can further simplify this one. We have two expressions, cn and second one is c minus n, and summation is changing from n equal to 1 to infinity. So the final complex Fourier series is given by 15. In this one, f of x is equal to summation over n minus infinity to plus infinity cn e raised to power iota nx, where cn is given by 1 upon 2 pi minus pi to pi f of x e raised to power iota nx dx, and n is taking values 0 plus minus 1 plus minus 2 and so on. In this one, the second expression in the first line, c minus n e raised to power minus iota nx, this one is appearing in this final expression 15 when n is taking values from minus 1 to minus infinity. So 15 is the final complex Fourier series for a periodic function with period 2 pi. Similar to this expression, we can rewrite the complex Fourier series for a periodic function with a general period p equal to 2l, and it is given by 16. F of x is summation over n minus infinity to plus infinity cn e raised to power iota n pi over l x, where cn is given by 1 upon 2l minus l to l f of x e raised to power minus iota n pi over l x dx. Just take care of one thing, the sign of exponential function in these formulas. Consider a numerical problem for complex Fourier series. Let f of x be e raised to power x defined from minus pi to pi, which is periodic with period 2 pi. We have to find out its complex Fourier series, and from the complex Fourier series we have to find its usual Fourier series. Write down expression number 15 and we have to find out what is Cn. Cn is 1 upon 2 pi minus pi to pi f of x e raised to power iota n x. Combine the exponential function e raised to power 1 minus iota n x dx. Integrate it. We can simplify this expression. See the underlying expression for exponential functions. E raised to power minus iota n pi and second e raised to power iota n pi. We can simplify this one. It is cos of n pi minus iota sine of n pi. Sine n pi is 0 and cos of n pi is minus 1 raised to power n. So we can simplify this further and we have this second last expression, e raised to power pi minus e raised to power minus pi, and this is 2 sine hyperbolic pi. So finally in 7 we have the complex Fourier series. Now from this we have to find out the usual Fourier series. We will do something similar whatever we did for finding the complex Fourier series. We substitute the value of exponential function e raised to power iota nx in terms of cos and sine. Now we simplify the complex Fourier series and we rewrite everything in terms of cos and sine. Start with the first one. 1 plus iota n e raised to power iota nx. Put the value of exponential function e raised to power iota nx. Multiply this. We have real part as cos nx minus n sin nx plus imaginary part as n cos nx plus sin nx. Similarly, for negative integral values, we can simplify this expression. 1 minus iota n e raised to power iota nx. And to simplify this, we just replace iota by minus iota in the second expression on this slide. So now we just substitute these values in the complex Fourier series. For n equal to 0, we keep it separately. For positive and negative values, we just combine the values. For example, n1, minus 1, 2 and minus 2. So we have finally this expression summation over n 1 to infinity minus 1 raised to power n divided by 1 plus n square 2 times cos nx minus n times sin nx. This expression is obtained by adding the second and third expression above. So finally we have the Fourier series in terms of cos nx and sin nx, and we can read what is a0, an and bn from this expression. Now try just one problem. Find the complex Fourier series for the periodic function f of x, which is x square defined from minus pi to pi and its period is 2 pi. For any given periodic function with period 2l or 2 pi, we can find out its Fourier series, which is in the form of an infinite series. But we always prefer to work with finitely many terms. So rather than working with infinite Fourier series, we try to use finitely many terms of this series. So this leads to the next topic, approximation of a given function by trigonometric polynomial. Fourier series play a very prominent role in approximation theorem. We can approximate a function by trigonometric polynomial. So let's start with the function f of x, which is periodic with period 2 pi defined on the interval minus pi to pi. We can write its Fourier series as f of x is equal to a0 plus summation over n 1 to infinity an cos nx plus bn sin nx. If we see this expression, the number of terms in the summation is n is from 1 to infinity. So rather than working with this infinite series, if we take finitely many terms, we call that one as nth partial sum, means sum of n terms. Then the Fourier series can be written as a Fourier polynomial, which is a naught plus summation over n small n from 1 to capital N. An cos nx plus bn sin nx. I am representing this by number 17. See the expression on the right hand side. This is Fourier polynomial. On the left hand side we have f of x, but in the center I am writing approximation sign, because from the Fourier series we have eliminated or truncated some terms starting with n plus 1, n plus 2 and so on. So they may be equal, may not be. So we say that the expression on the right hand side is an approximation of the given function f of x. Now the question is, we can have any other approximation of this periodic function f of x in terms of trigonometric polynomial. So we want to find out that which of the trigonometric polynomial approximation is best for a given periodic function. Now we will prove that Fourier polynomial approximation is the best trigonometric approximation for a periodic function f of x. To show this, we will approximate the function f of x by any other trigonometric polynomial, and then we show that the error is minimum if this trigonometric polynomial is Fourier polynomial. So let's note by capital F of x as a naught plus summation over small n 1 to capital N cos nx plus capital Bn sin nx. Equation number 18. Let this be any other trigonometric polynomial approximation of the function f of x. Then we will calculate the error for the function f of x on the interval minus pi to pi. Now we define the error. We can define the error in terms of difference of the function and its approximation. We can take its mod also. Here we are taking error as a total square error, and we are defining it as integration from minus pi to pi given function f of x minus capital F of x whole square dx. Equation number 19. Clearly this error e is greater than or equal to 0. So now we simplify 19. For given capital N, which is fixed, we want to find out the coefficients in this trigonometric polynomial approximation given by a naught, capital An, capital Bn, such that the error e given by 19 is minimum. So we simplify the right hand side of 19. We can simplify the square and we have relation number 20. In this one, we simplify further star and double star expressions. Now we simplify capital F of x whole square. This expression is something like a plus b plus c whole square. Before we start the simplification, I am changing notation in the second summation with bn sin nx term. I am rewriting this one as summation over m 1 to capital N bn sin mx, because on simplification we have to multiply cos terms and sin terms, and they can have different arguments, like cos x can be multiplied with sin x, sin 2x and other way also. If we keep the same notation, then we will get product as cos nx and sin nx, which is not so. So apply the formula. We have second expression on this slide. We can say it is a square plus b square plus c square plus 2ab plus 2ac plus 2ab. In the last one, we have double summation n from 1 to capital N and m from 1 to capital N. Now we just simplify the second and third term again in this expression, because again we have summation and then whole square. So we can again simplify this one, and we have the next expression a naught square plus terms with an square cos square nx plus 2 times summation over an am cos nx cos mx. Similarly, we have the next one, summation over m 1 to capital N bm square sin square mx, and then 2 times summation over mn from 1 to capital N bm sin mx sin nx, and the remaining expression as it is. Now we just integrate this expression on both sides from minus pi to pi. While simplifying this, we will use the property that the trigonometric system is orthogonal. So I have marked the expression. We use orthogonality, and after integration from minus pi to pi, all these expressions will be 0. Now integrate capital F of x whole square from minus pi to pi. I have marked various expressions. Their value is 0 because they are orthogonal. And we have just 3 expressions which are non-zero. 2 pi times a capital A naught square plus summation over n 1 to capital A n whole square pi plus similar expression for bm. In this summation, you can write down summation over m from 1 to capital N or from n 1 to capital N. It hardly make any difference. So after simplification, we have equation number 21. Now to calculate the next expression in the error, we multiply the capital F of x function by small f of x. That is equation number 18 by small f of x. We have the next equation. Now integrate with respect to x from minus pi to pi. Now we have the last expression. See these expressions which I have underlined. The expression with the capital A naught, it is 2 pi times A naught. With capital AN, the expression is pi times small an, and with capital BN, we have pi times Bn. These are Fourier coefficients. So finally, after simplification, we have equation number 22. Now we substitute equation number 21, 22 in 20, which is the expression for the total square error, and finally we have relation number 23, that the error in approximating your periodic function f of x by any trigonometric polynomial whose coefficients are capital A naught, capital An, and capital Bn. Now we calculate the error if we approximate our given function f of x by a Fourier polynomial. For this, we don't have to do the calculation again. We can calculate this from expression 23. In that case, we just replace capital A naught by small an, capital An by small an, and capital Bn by small bn. Let's represent this error by E star. First expression in equation number 23 will be as it is. Second and third expression in bracket, we can just simplify them by replacing the above said command, right? So equation number 23, E star, it is the error when we approximate a function by Fourier polynomial. Now subtract error E star from the error E. We have the first expression. Now we try to simplify this. I have marked various terms and underlined them by putting star and some underline curves. So we combine these similar terms like capital A naught, small a naught, capital A n, small a n, and capital B n and small b n, and we have this second equation. Now we can further simplify this one, and finally we have the third equation on this slide, that E minus E star, this is equal to 2 pi capital A naught minus small a naught whole square plus summation over n 1 to capital N an capital An minus small a n square plus capital Bn minus small bn whole square. Clearly, right hand side of this above equation is always greater than or equal to 0. So we can say that E minus E star is greater than or equal to 0, and hence E is greater than or equal to E star. So it proves that the error in approximating a function f of x by any trigonometric polynomial is always greater than or equal to the error when we approximate our function by Fourier polynomial. So we can say that error is minimum when E is equal to E star. So this is the proof of the result that Fourier polynomial approximation is the best approximation. So finally we have very important theorem, minimum square error. It tells us that when we approximate a function f of x by any trigonometric polynomial, then the error is minimum if and only if the coefficients of the trigonometric polynomial are Fourier coefficients, or we can say that Fourier polynomial approximation is the best, and the error E star is given by equation number 25. Now very important observation here. The first term in this error is integration from minus pi to pi f of x square dx. For a given function, this expression is always going to have something finite and constant value. But in the second expression, we have capital N. So we can approximate the polynomial by any number of terms, maybe 3, 4, and so on. So the second expression in 25, it will increase as we increase the number capital N, and every time we are subtracting something more from the first expression. So we can say that the error will decrease as we increase the number of terms in the Fourier polynomial. Every time we get a better approximation, and as capital N tends to infinity, error will tend to 0. This is the geometrical view of the approximation. Let's consider this function f of x, which is x plus pi, defined from minus pi to pi, and its period is 2 pi. So the first graph is the graph of the function f of x. You can find out its Fourier series. I'm just writing that part. Pi plus 2 times sine x minus 1 by 2 sine 2x, and so on. So we can approximate this function by various partial sums. I can say s1 pi plus 2 sine x, then s2, it means number of terms up to n equal to 2. We can approximate by s3 and suppose s20 also. Now see the second graph. I have the graph of the function from minus pi to pi. Then for s1, s2 and s3. So see the first red line, it is s1, and you can see there is a lot of error between the value of the function and s1. Then see s2, there is again error, but it is less than s1. Similarly for s3. Now come to S20, the last graph. If we draw S20 from minus pi to pi, this is the graph, and in black color I have the graph of my actual function, and you can see that S20 is much better than S1, S2 and S3. So as we increase the number of terms in approximation, finally the approximation will tend to the function f of. From this theorem we have very important inequality, in fact two, Bessel's and Parseval's identity. We know that error E star is always greater than equal to 0, and it holds for every value of n. So we can rewrite that error formula, that 2 times a naught square plus summation over n 1 to infinity a n square plus b n square is always less than equal to 1 upon pi minus pi to pi integration f of x whole square dx. In this one, the summation is from n equal to 1 to infinity, because we are saying that this result holds for every value of n, even when n tends to infinity also, right? So as n tends to infinity, the Fourier polynomial will tend to Fourier series, and hence error will tend to 0. So in the Bessel's inequality, we have now equal to sign, and we get a new identity. We call this one as Parseval's identity. This is very important. We will discuss numerical problem based upon this identity. Consider this example. F of x is mod x, defined on the interval minus pi to pi. It is periodic with period 2 pi. We have to find the Fourier polynomial for f of x for capital N equal to 1, 2 and 5. From the graph, we can see that function is an even function. So for this, we have Fourier cosine series. We calculate just a naught and an. A naught is pi by 2. An is 2 upon pi integration 0 to pi x cos nx dx. Simplify this expression. Now depending upon n is even or odd, we have the value of an 0 for n even, minus 4 upon n square pi for n equal to odd. Now we can write down the Fourier polynomial approximation. f1x a0 plus a1 cos x, put the value of a1, f2x a0 plus a1 cos x plus a2 cos 2x, substitute the values. Now error E star is given by minus pi to pi f of x whole square dx minus pi times 2 times a0 square plus summation over n from 1 to 3. I am doing this calculation for f3x. So put all the values, simplify this. Finally we have error E star. You can see the last expression on this slide. Now very important numerical problem. Questions related to Parseval's identity. Consider function f of x, which is mod of sin x, defined on the interval minus pi to pi. F of x is periodic with period 2 pi. So we have to find its Fourier series and hence find the sum of the series given below. You can draw the graph of the function. This function is an even function, so we will find out its Fourier cosine series a0 plus summation over n 1 to infinity an cos nx. Write down the formula for a0 and an. Put the value of function. Integrate this. A0 is 2 upon pi and an is, I have shown the calculation part, So after simplification, an is 0 if n is odd, and if n is even, it is 4 upon pi times n square minus 1. And the Fourier series is given by star, where we are taking summation over n even integers, positive integers. Now to find out the sum of the required series, there are two options. First, we try to get the required series from the Fourier series directly. But here you can see you can try 0, pi, minus pi, plus minus pi by 2, but we don't get the required series. So in such cases, means when we can't get the required series from the Fourier series directly, then we have to use Parseval's identity. Then Parseval's identity is, I have written here. So just put the values of a naught, an, bn is 0. We have to just simplify the right hand side, that is minus pi to pi integration of f of x whole square dx. Simplify this, we get the desired series and we have the final answer. Try following examples. For given function, find out its Fourier series and hence find the sum of the given series. You can find out the sum directly by the Fourier series. If you are not able to get the series, then you have to use Parseval's identity. Now one more example I am discussing here. Using Fourier series, find the value of this integral minus pi to pi cos x raised to power 4 dx. You can easily evaluate this integral directly, but now we are doing this using Fourier series. So we define a function f of x. This one is cos x whole square. This is a periodic function with period 2 pi, hence we can find its Fourier series. No need to do the calculation, you can directly write down the formula that cos square x is 1 plus cos of 2x divided by 2, which is 1 by 2 plus 1 by 2 cos of 2x. So this is the Fourier series of the function cos square x, and this is a finite series. All the coefficients ai's and bi's, they are 0 for n not equal to 0 and 2. Now we use Parseval's identity, which is 1 upon pi minus pi to pi f of x whole square dx. This is equal to 2 times a naught square plus summation over n 1 to infinity an square plus bn square. Put all the values, that is f of x, a naught, ai's and bi's. Simplify this and finally we get its value as 3 pi by 4. We can evaluate other complex integrals also, but this is one of the important numerical problems.